But anyway, let me introduce Riley Blocker. Who'll be giving this defense today. He came to the University of Miami in 2018, we figured out. A couple years before the pandemic or so. It's been an interesting time at the university for graduate students, I think, especially for Riley, which because going to field trying to get through the COVID requirements. So it's been sort of a hassle through the years. Let me first tell everybody what the format's going to be, because so there's three parts to the defense here. First, we'll have a presentation by Riley, and then the room will be open to questions from the class. And then after that, excuse everybody at the committee and we'll have a short time of questions between the committee and Riley. And then Riley puts it to making this. So that's the format. And so you're right.
Great, thank you so much. And I do have a lot of appreciation to be here. There's a lot of things I knew I loved, like the ocean and being outside, but then I found out more I liked, all related to the ocean. So it's really been a privilege. And today I'm going to be talking to you all about what I've done through my work here at the University of Miami, and that's measurements of the distribution of polarized light. And of course, today's September 11th, and I just would feel amiss if I didn't say some sort of appreciation for our country on this day, but it's good to go ahead and get started. Let me figure out. Okay, so I'd like to start with a question I can't answer, and that is, what is light? So I can't give a good answer to that, but one person that can give a good answer is Maxwell. He has his equations stated here. They're in a vacuum, and what we can do with these equations is formulate them and graph them out pictorially, and we have a graphical representation of what light is. What to note here is there's an oscillating electric field that's shown in red, and perpendicular to that, there's an oscillating magnetic field labeled B here. And given this pictorial representation, we can relate some of the properties of light to it. By convention, usually you either choose the electric field or the magnetic field to reference to. So for simplicity, only the electric field is shown, but we can relate some of the properties to this diagram. So amplitude is related to intensity, and we're all familiar with intensity just being the brightness of light, but that's how it would relate to this representation. Then color, which we also see with our eyes, is related to wavelength, which is just this distance measurement here, which is the distance between two peaks. And of course, what we're going to be talking about today is polarization, which just points in the direction of where this electric field is oriented. So the reason I kind of quickly went through all these is just to say, with this simple representation, there's nothing more daunting about polarization, to me at least, because to me, wavelength and amplitude look just as abstract. There are reasons why amplitude and wavelength are easier to measure than polarization, but relating it to something in the physical model, they all look equally more or less complicated. So just because we have familiarity with color and brightness with our eyes, I don't think there's too much to be daunted with polarization. So given that we're going to be talking about polarization, how are we going to mathematically describe it? So shown here is another electric field, but now in an arbitrary general direction. So what we can do is sum up the contribution of this electric field in two perpendicular planes, and we can do that both in the x plane and the y plane. So mathematically, given a wave equation, we have a general wave equation highlighted in yellow here, but what's important to note is this directional component. And this directional component, as I said, is just the summation of the two different perpendicular contribution in the two perpendicular planes. So that's how we can mathematically describe linearly polarized light. And that's relatively pretty easier than what we might be used to seeing. And so why do we ever complicate things? And that's because this representation works great for linearly polarized light, but there's also different polarized states. So you can have unpolarized or any state in between. So we introduced something called the Stokes parameters, or found out by Stokes, that really handles all these cases a lot better, whereas this representation can't. So just to kind of reiterate and show what different polarization states might look like for linearly polarized light, we again are showing a linearly polarized plane wave, and that's oscillating all in one direction, so it's fully linearly polarized. But of course, you might have a random distribution of electric field vectors, And then that also requires different phases and frequencies for it to be truly linearly unpolarized, which as you can see, it's kind of, there's no systematic orientation of the electric field wave. So that would be completely unlinearly polarized. And of course, given those two extremes, you could have any state in between where we have some distribution among a direction, but it's not necessarily, there is some sort of preferred orientation, and that would be a partial state. Now, so to handle those partial states, we're going to have to introduce the Stokes parameters. And just to define it here, this is, I think, the quickest way to introduce it is just geometrically. So this red ellipse here is the way a electric field vector will trace itself out in time. And so then you can geometrically relate to the properties of the ellipse given this angle here, which is chi, and also this beta parameter. So quickly, just stating what the Stokes parameters are, we have I, Q, U, and V. I is related to the irradiance, which is kind of brightness, and that's kind of a concept we all should be familiar with. Q and U are related to the linear polarization, and then V is related to the circular polarization. So if we look at that beta term, we can see as beta increases, the V component would get a lot more weight, whereas if V shrinks down, V would disappear, and we're only left with Q and U, and that's what we're going to be talking about in this presentation is linearly polarized light, because that's what our instrument measures. And then the remaining term, we see how beta affects the equations. The remaining term is the angle linear polarization. So the shift between if you have more Q or U given linearly polarized light is dependent on that chi term, and it just weights in between the two. And then just to kind of further visually see what's going on, again, like I said, the general state of light is elliptically polarized, and so that's how we get those ellipses that we're defined our Stokes parameters to. It's just how it traces out in time. But of course, since we're dealing with linearly polarized light, that ellipse contracts, the semi-minor axis goes to 0, and we're just dealing with linear oscillations. And then given the Stokes parameters, we can get to a far more intuitive concept really quickly, and that's the degree of linear polarization and the angle of linear polarization. So for the degree of linear polarization, if you have the Stokes parameters, you can compute it with this simple algebraic formula and then get how linearly polarized the light is. If the output was 0, you have completely linearly unpolarized light, whereas if the output's 1, your light's fully linearly polarized, and of course any state in between for any value between 0 and 1. And then given linearly polarized light is pointing in some preferred direction, and that's what would be given by that chi term there. And again, just to see the Stokes ellipse for linearly polarized light, it wouldn't be a true ellipse, it would be collapsed in on itself. And so it's kind of the simple geometric relation here. Now, when you define an angle, you need some sort of reference plane. And so you choose one and you want to do it concretely, and that way you can always know what you mean when you say something's 45 degrees or 90 degrees. So all our field data is going to be in the meridian reference frame. It makes a lot of sense for when you're taking pictures of the sky or the ocean. And that's going to be defined by, here in this case, Z pointing along the zenith direction, and also along with the vector pointing along the direction of the light beam you're talking about, which is this I vector here, which is in red. So given those two vectors, you can draw a plane, which is that kind of shaded red region. And with that plane, you then define two coordinate axes, the R and L. So R is for perpendicular, that's perpendicular to the plane. L is parallel to the plane. And then, so all your angle and your polarization measurements are the angle of the semi-major axis of the ellipse measured from L approaching R. Okay, so we have a convention for talking about linearly polarized light. How do we measure it? And we measure it. We're measuring it with this instrument here, which we call Pixpol. And to highlight some of the technologies on Pixpol, one of the main things is the use of a fisheye lens, and that gives you a really wide field of view. So in one image, you can quickly image most of the scene, almost a full hemisphere. And we use 4 of those cameras. And if you look in the center picture, we can see a few of those cameras mounted to their plate, and then they're sealed up on their watertight housing on the right. And those 3 cameras we can kind of see here, they have a spectral bandpass filter behind the lens to characterize the wavelength of light, and we have blue, green, and red channels. And those 3 cameras are pointing straight down, just submerged just below the ocean, And those are what measures the upwelling light signal. We do have one more camera at the top of Pixpol, so in that image at the bottom, it would be pointing straight up towards the sky in the zenith direction. And we also have sky measurements, but there's only one, and we're measuring 500 nanometers with that camera. Now, like as I highlighted, the fisheye technology is pretty useful in our case. So I'm going to walk through what an image from Pixpol looks like to then be able to relate it to what was going on in space. And that's done with this kind of simple equation, r prime equals f theta. And we can kind of see how those terms come about with this representation here, where it would be a fisheye lens is placed at the origin, and it's imaging down to the image plane, which is the dotted lines at the bottom of the screen. So given an object, which is defined in 3D space with three parameters, theta, phi, and r, that is going to be projected onto the image plane, and now in 2D space with just r and phi prime. So here's a real image taken with Pixpol of the University of Miami. And using that relation, we can kind of orient ourselves in the 3D world of what was going on there. So at the very center of the image will be a straight on viewing angle. And as you get farther and farther away from the image, you have a higher viewing angle. So it's a fairly intuitive lens to kind of relate things back in space. And now, when dealing with polarization, it can kind of get muddled and confusing when I'm showing images of what's really going on, but hopefully this might help explain it. So I'm calling this the natural perspective of the atmosphere-ocean system. So given an observer at the center, they can either look straight up or straight down. And if they're looking straight up, here's where the sun would be. So this is only half of the sphere. I'm only showing things on our side of the sun, looking at the screen, but it is the world's 3D, so it would rotate around, but I can only show half of it. And then given the sun, we also have the anti-sun. So this diagram takes into account a flat air-water interface on the XY plane. And so the sun is refracted a little bit by the interface. And so that angle is going to be a little bit closer to the Z-axis than the sun was to the negative Z-axis. And that's going to become important, and that's why I'm talking about it here. And then here's the principal plane, which is really important to relate properties of polarization, because ideally, in the ideal case, everything is going to be symmetric on the other side of the principal plane. So it's important to know where that is, but that's defined as the zenith and sun direction. So you get that plane there. And then Stokes parameter Q equals 0, and Stokes parameter U equals 0. If you trace those out, this is the distribution you would get in the sky. These are in the meridian reference frames. So your eyes would, even if you could see polarization, wouldn't see it this way, but this is kind of an idea of what things might look like. And what's to note is when Q and U are both 0, so where the lines intersect, that gives a degree of linear polarization that's 0. So there would be no linear polarization there. We call that a neutral point. And in this, it's occurring right at the sun. These lines were modeled with just unpolarized light from the sun, scattered with a Rayleigh model straight to an observer. But as we can see down here, something a little different happens. And that's because the unpolarized light from the sun was transmitted through the flat air-water interface, which imparted a little bit of polarization to the light beam. And that actually takes that neutral point and splits it into two different directions along the principal plane. And so we see this separation of where the neutral points are, again, defined where those white and gray lines intersect. Sorry, black and gray lines intersect. So this might be how things look in the real world, but with a fisheye lens, I'm going to try to show what we would see with Pixpol. And so given these two hemispheres, we split it between the downwelling contribution, which is the sky, and the upwelling contribution, which is looking down on the water. And we have these two images here. The neutral lines are shown again here, but I've also just shown the degree of linear polarization as well, which wasn't in the last image. But again, we can see where the sun's located, and that's going to be in the downwelling image, and the anti-sun in the upwelling image. Then the principal plane in this case is just horizontal along the x-axis, and now we can actually see on the other side of the principal plane, which we couldn't see earlier, but you can see the symmetry of these neutral lines. And again, the neutral point where we can look at where these white and these U equals 0 and Q equals 0 lines intersect, it's occurring at the sun in the same fashion we saw in the earlier image. Whereas down here, again, we see the splitting of the neutral points. It's still along the principal plane, but it's not occurring at the anti-solar location. So this is in real life with pixel measurements, we're only seeing the right side of this slide as far as how we relate the polarization properties of the sky and water to what's really going on. Okay, so now I'm going to talk a little bit about, given an image from Pixpol, how do we actually get the polarization properties from that image? So one of the other kind of key technologies to Pixpol is the use of a division of focal plane polarimeter. And that's where over each pixel, there's its own individual linear polarizer. Pixpol has almost over 2,000 by 2,000 pixels. So it's over 5 million pixels overlaid with its own individual linear polarizer in one of 4 directions. So with one image, you can take those 4 linear polarizer groupings of pixels and collapse it into those Stokes parameters, because that's enough to give you the first 3 Stokes parameters. And that's what we do. And so the technology there is just one image with one camera can give you the distribution of IQ and U. And that's a commercially made camera that we use that uses that technology. And so to kind of show how this is really helpful, I have a setup here with a rotating subject. And so the subject's moving, the camera's staying still. And for this first method, I took a picture behind a linear polarizer, rotated the linear polarizer, took another picture, and repeated that for a 3rd time. Combine the images together and retrieve the angle of linear polarization. As you can see, we do get some detail here. Or I should also mention what I'm actually taking a picture of, and that's just the light source, which is my phone, and a cardboard cutout of the letters Pixpol. Between those are the linear polarizer. So the light coming out of those letters is linearly polarized. I rotated the linear polarizers kind of randomly across the letters. And so we want to retrieve that linear polarization with Pixpol, and we see kind of a first attempt at it here using the method I just described. However, because we have a division of focal plane polarimeter, we can get that same information from just one image by collapsing those subpixels together. We have a much cleaner, crisp image, which obviously, if you're out in the field and your instrument's on the water, it is moving. So you want to get the data as quickly as possible so you don't have that same blurring we just saw. And in the lab, this is going to be how we actually relate the signal from Pixpol to an actual linear polarization. So here's a diagram of the setup. We have Pixpol, and it's imaging an integrating sphere, which is a source of unpolarized light. Between the two, we have a linear polarizer. So the light Pixpol sees is linearly polarized in the direction of our linear polarizer between Pixpol and the integrating sphere. And here's the real image that Pixpol just took of the setup. And we can see the integrating sphere is at the center. It's kind of, because we have a fisheye lens, even though Pixpol is fairly close to the integrating sphere, the field of view is so large, it's only covering a tiny region of the field of view, and that's going to become important later. But if we zoom in, we can start to see the pixel structure of Pixpol emerge until we get to the pixel level, where these 4 squares are 4 individual pixels, and we can see the different signals this one linear polarizer orientation gave. So in the top left pixel, the linear polarizer in front of the integrating sphere was perpendicular to the linear polarizer in front of that pixel, whereas in the bottom right corner, those linear polarizers would be parallel to each other, and we'd have transmission of light. And then the 2 remaining pixels are in some state in between. And what we do is we separate out those pixels based off what linear polarizer they have in front of them, and we can form the full image again, but 4 different classifications of that image. And so as I take an image, I rotate the linear polarizer in front of Pixpol, and I do that for 18 or so angles, and I kind of can loop through and show what that would look like for the responses of the different subpixel classifications. So it alternates between complete extinction and complete transmission. And we have numbers to relate to that signal. Cameras have counts, and so we can plot the signals here with the linear polarizer angle in front of Pixpol. So the x-axis is the linear polarizer angle, and R shows the signal of each of these subpixels groupings. And so this is kind of hinting at how we can take data from Pixpol and get meaningful polarization images from it. For example, if we look at 45 degrees, we see that one pixel had a very low signal, whereas another pixel, the green line, had a very high pixel. And then the remaining 2 pixels were about midway in between and roughly equal to each other. If we look at where those ratios of pixels appear again, they don't. So if we're out in the field and imaging a scene and we see that kind of similar ratio of pixel signals, we can say that's 45 degrees of linearly polarized light. And that's exactly what we do. Now, I mentioned earlier, the integrating sphere is only filling a very small portion of the total image of pixels. So if we're out in the field and we have an image that fills up that entire screen, how do we know that our calibration data applies to those higher viewing angles? So what I've done is I took Pixpol and formed a composite image. I had the Pixpol pointing at the integrating sphere as we just saw, and I rotated it, took an image, and continued that, and that made a horizontal sweep across the image. I then rotated Pixpol along its azimuthal axis and did the same thing and repeated. The reason we do this is because now this composite image fills the entire field of view of Pixpol, and we can see how our calibration data works for these higher viewing angles. So here is the full field of view of Pixpol of the integrating sphere of that composite image we just showed, and I retrieved the angle linear polarization using our polarization calibration. As you can see, this looks fairly bad. I was not rotating the linear polarizer in front of Pixpol, so we would assume that it would all be the same angle. But one thing to keep in mind is that I was rotating Pixpol to actually fill the field of view of the entire image plane. So each of those rotations changes our reference axis, and so we have all possible orientations of linearly polarized light. So all I can do, or what I can do here, is just subtract out how much I rotated Pixpol. So if there's a sweep where I rotated Pixpol 45 degrees, I would just subtract that 45 degrees. And then that image would be more of what we see here, which is a lot better. Instead of having every possible angle linear polarization now, it's more across a distribution between minus 10 degrees and 10 degrees. And the linear polarizer angle was 0. So we're hoping for 0, and that's kind of the spread around 0. But still, even though that's a lot better, it's still not fantastic. And that's because there's one more thing about a fisheye lens we need to kind of account for here, and that's the distortion. So all camera lenses have some sort of distortion, and that's usually due to imperfections or impurities in the lens. And fisheye lenses certainly have those too, but this distortion is strictly using that R equals F theta projection. Anytime you take a 3D scene and image it on a 2D plane, something's going to have to give or take. And the mathematical relation gives a really defined way that happens, but it causes things to appear differently. So here's an image of just a checkerboard with one of the fisheye lenses. And as you can see, in real life, this checkerboard had perpendicular intersections between the grid, but here we have some curvature. And that curvature we need to account for because the linearly polarized light would also experience this similar sort of curvature. So what we've done, and with the help of my advisor, he just had a trigonometric or geometric argument for how a straight infinite stick in space would be imaged with a fisheye lens. So this stick is in red, and on the image plane is what the image of that stick would look like with a fisheye lens. And as we see, that stick is not straight on the image plane. There's definitely some curvature there, and that's the same thing that's going to happen to our linearly polarized light for these other higher viewing angles. Whereas you can see in the center, along the y-axis, that stick is roughly the same orientation we would expect. It's still perpendicular to the y-axis, but as we go way away in the higher viewing angles, it does rotate some, and so we need to account for that, and we do that. And now instead of plus or minus 10 degrees, we get plus or minus 5 degrees, which is certainly an improvement, and it's actually better than that because those are the max and minimum pixel values. So what we can do is take all this. Okay, guys. Little ears, I guess. But anyway, we can take all those pixels and make a distribution. So we would expect the distribution to be 0. We want it to be around 0, which we see with all the means. And this is, well, the plots are the red, green, and blue are from each of the 3 upwelling cameras. And so they all kind of agree with one another, which is good. And we look at the standard deviation, we can get an idea of the uncertainty in our retrievals. And then using that composite image, I can also kind of see the spread in Stokes parameter I and the DOLP. I did not have to go through this data and do the corrections I applied to the angle linear polarization because these parameters are not reference frame dependent. So essentially rotating Pixpol does not have an effect. And so none of those steps needed to be taken for that. And that's part of the reason why we see the degree of linear polarization look a lot better than the angle linear polarization because there's nothing to really correct for. And so we see a very small standard deviation there. And then in summary, I can just state the uncertainties. These we call them the inner variability of these parameters across the entire sensor. And we can kind of expect plus or minus 5% for I, 0.04 for Q and U over I, and then 0.01 for the degree of linear polarization, and 2 degrees for the angle of linear polarization, based off the standard deviation of the histograms we saw. Okay, great. And now I can finally get into some measurements with PixPol. And this is real data taken out in the Florida Keys the spring of 2022. And so shown here is just a map of the chlorophyll A concentration. And really all I'm doing here is just showing we did take pictures of a variety of water types. We have some open ocean locations, stations 1, 2, and 3, all fairly close together, but you can see that it's drastically different than station 4, which is very close to the coast. It's going to have much different water. And thank you to Dr. Mike Twardowski's group for inviting me on this cruise to get this data. And then here's the image of kind of our setup. This is one of the open ocean locations. You can see the boat we were on with the laptops and PixPols tethered and hanging behind the ship. And one thing that was really nice about this day in particular, if we look at station 3 in this graph, we can see how many solar zenith angles we really got. So we were out at maybe 9 or 10 a.m. The sun was close to the horizon, maybe 65 degrees. And then we waited all day with really good sky conditions until the sun got really close to zenith. And so we have a nice distribution there. And of course, here's the other locations. But this plot is just showing where we have data at the different locations according to the solar zenith angle, which is kind of a proxy for the time of day. And for this first image set series I'm going to show is just for this one location across time. And I'm starting with what is hopefully the most intuitive, and that's Stokes parameter I, which is just how bright things are. So if we look on the left, that's the downwelling camera looking at the sky, and we see the sun track across the sky in time. So from that 65 degrees solar zenith angle to about 10. Similarly, on the right, we see the brightness of the scene with Stokes parameter I, and that's for the upwelling light, just beneath the surface. What we see track across there is the anti-solar location, which is kind of specified by the shadow cast by PixPol. So if the sun's up in the sky, it's going to hit PixPol, and then down after it gets refracted through the interface, it's going to show where that anti-solar location is. And we see that track across the image as well. And then I is not necessarily what we're really interested here in this case, because we want to show the polarization. So this is the same images, but now we're showing the degree of linear polarization as it changes with time. First thing to kind of note is that we have a maximum for this field of view in the sky of about 76%, whereas in the bottom or in the upwelling image, we have a decreased linear degree of linear polarization. Another thing to note too is maybe when the sun's really close to the horizon, you can see the field of view is filled a lot more with these 90-degree scattering angles, which is where we would expect sort of the maximum to be. So we have a lot more data that's really well defined. But as the sun gets higher in the sky, the field of view is filled up with more of these scattering angles closer to the anti-solar point of the sun, which is where we have a lower signal. And so you can see the lines kind of get a little bit more noisy in that case. But the higher solar zenith angles look a lot better. And then again, we can show the angle of linear polarization. Kind of like one of the kind of interesting things to note here is that actually the angle of linear polarization is fairly robust and constant. You could kind of envision if the sun was covered, but you knew where you were looking, you could kind of guess where the sun is. And it turns out that the animals that can detect polarization, like some birds, bats, and bees, when they do detect polarization, what they use for navigation, the property of polarization is the angle of linear polarization, because this is relatively predictable, even with different conditions. Okay, so what we can do with this data is compare to a single scattering model. And again, I said it before, but I'll briefly run through it again. We take unpolarized light from the sun, transmit it through a flat air-water interface, which changes the angle of light and also changes the polarization state of that unpolarized light. And then we're going to scatter it up towards the observer using the Voss and Fry 1984 average ocean Mueller matrix, which is generally well representation of the open ocean location we were at. So on the top, we can see the degree of linear polarization using that model, and using the input of a 64-degree solar zenith angle, which was the same solar zenith angle as the actual measurement at the bottom of the slide. With the theory, we can get a full 90 degrees field of view, but Pixpol can't do that. So if you look in the top, you see a circle of white and black lines, and that shows the field of view of Pixpol. So if we look at the anti-solar location in the theory, we see that it occurs right at the edge of the field of view of Pixpol. Of course, when we look at the Pixpol measurement, things geometrically line up because we see the anti-solar point occur at the edge of the field of view. And what I'm going to note, and then, sorry, I also have just shown the angle of linear polarization too. And what we can note as we just advance through these slides is just, again, what I hinted at earlier, is that things at the higher zenith angles, things look better defined, but as the sun gets closer to the zenith, things get a little bit more noisy, but interesting patterns and shapes do emerge. And of course, this is with the sun being really high, and I don't think Pixpol could ever really differentiate what's going on there. Okay, so that's with one location with that previously was one location with all the solar zenith angles. Here's different locations with the same, the best we can do solar zenith angle. And that's because, as we saw, the solar zenith angle really affects things. So when we're comparing these locations, it just definitely helps to have a similar solar zenith angle across them all. So these are kind of the data points we'd be looking at here. And it's just shown, here's all the different locations with approximately the same solar zenith angle. And just, I'm going to highlight a few features. One would be at station 2 in the top right of the slide, we had a lot of cloud cover, and that covers the top half of that image. And as you can see, that cloud cover kind of obviously changes how the signal looks, and notably the symmetry across the principal plane. So the x-axis, we obviously don't see what we see at the bottom of the image at the top of the image because those clouds are there. Similarly, in station 4, we have cloud cover. It's much more diffuse and random, but that's also why we would see a drop of the degree of linear polarization there. Whereas stations 1 and 2, there's not clouds, as relatively clear, and so those are comparable, and we see very similar results. And we can keep those points in mind as we look at the upwelling polarized distribution that was taken at the same time as those images. So again, if we look back at station 2, the clouds covered the top half of that image. And if we look here, there's no clouds in the water, but we can see the symmetry is likewise distorted, where the Q is a little squished in, the Q equals 0 line, and that's kind of what we see there. So I think the clouds are still having an effect in the upwelling data. In the bottom right, we noted some clouds, but we see a really, really low degree of linear polarization signal here compared to the other stations. And it's partly due to the clouds, I would think, but one of the biggest factors would be the multiple scattering events going on there due to it's in the turbid water location. So that is more frequency, a higher frequency of multiple scattering events definitely is playing a part in the overall lower polarization there. And then I think it's interesting too, as we previously said, the sky conditions at station 1 and 3, we look back, look fairly the same, but we're getting kind of a different polarization response in the upwelling light. So that could be a difference in the optical properties of water. Kind of what's to note is if we look at station 1, we have the intersection of the Q and U equals 0 lines occur roughly on the principal plane and between the anti-solar point and nadir. But at station 3, we don't see that same neutral point. We see it instead above and below the anti-solar point, which isn't predicted by our single scattering model and is different than that station 1 case. So that might be something interesting to study. And we're going to dive a little deeper and just show besides just visually looking at images, some metrics we can use to quantify what's going on here. So here's one of the images, and the simplest thing I could think of to do is take the principal plane and plot the degree of linear polarization with the scattering angle. So if it's 10 degrees or 20 degrees away from the sun, that would be the scattering angle. And for upwelling light is 180, 170, 160, and so on as you get further and further away. but we can plot that degree of linear polarization with the scattering angle along the principal plane. So again, at station 3, we had a really wide range of solar zenith angles, and each of those images is a line on this graph, and we kind of see some sort of distribution as the solar zenith angle changes, even though that we're looking at the same scattering angle, which is partly due to the polarization properties, of the atmosphere. And what we can do is compare these results to what a single scattering model predicts. And so this here is using the Rayleigh scattering matrix, and it looks very different. For example, at 90 degrees, you have a fully linearly polarized light, as one would expect with a single scattering Rayleigh model. We don't have that. It's just overall, the agreement's not that great, but we wouldn't expect it because we're using a Rayleigh scattering model, and it's a single scattering model. So those differences are expected. But when we replace the Rayleigh scattering Mueller matrix with the Voss and Fry average open ocean Mueller matrix, the fit looks a lot better, really good, I would think. And the first thing I would kind of conclude here is a lot of the depolarization, the departure from 1 we see at a 90 degree scattering angle, is due to the anisotropies of the molecules already identified in the Voss and Fry Mueller matrix, and not necessarily the more higher frequency of multiple scattering events. So this model, even though it's single scattering, just visually at this point looks fairly adequate to describe this open ocean case. Of course, what we want to do is see what we can exploit. I think it's nice that these measurements were done with Mike Twardowski's group, where he had his mascot instrument. So eventually we'd like to use his actual measured Mueller matrix elements at the time of this data collection and see how much that changes things. We can do 2 things with that. We can put it in this single scattering model and see if that's within outside the uncertainty of Higgs boson. But also ultimately, we would like to run those with Monte Carlo simulations to get into the discrepancies with these higher order scattering events. And then another thing I'd like to show is just the signal from the turbid water location, which is drastically different from our open ocean measurements and also both models. So there's definitely a difference there, and that should be exploited as well. And just differentiating different water types, because that's probably going to be useful. And hopefully that's drastic enough too to observe from space with remote sensing applications. And so I'm going to continue to talk about how we can quantify these polarimetric results from the images. Coulson was an atmospheric scientist, and he really said, given this distribution of polarized light, a lot of the information is contained in 3 things. One is the degree of linear polarization, and I think we kind of exploited that principle here. But the remaining 2 things are the location of the maximum polarization and the location of the neutral points. And I'm going to explain why I think these 2 things are kind of hard and difficult for Pixpol to do. So we might need to find a better way. One, for the location of the maximum is really going to always be outside our field of view. Even though the sun moving close to the horizon, once you account for refraction through the interface, it's going to get closer in to nadir. And then given that Pixpol is already kind of cropped in the upwelling distribution, that maximum is going to fall kind of outside the field of view. When it is inside the field of view, it's going to be close to the edge, and it's going to be an unreliable prediction to declare that a maximum. Then there's the location of the neutral points. But if we look at this image here, the neutral points are occurring, in this case, near the anti-solar point, but a few things are going on which makes that tricky. One, that's where the shadows cast by the instrument, and that's going to change the contribution of diffuse and direct solar light. And I don't really know how it plays into effect, although a Monte Carlo simulation will help with that. The other thing is that by definition, neutral points are where there's very low polarization signal, in fact, none. So the uncertainty in our measurements are going to have the greatest relative weight there. And we see that get noisy where those lines are more unpredictable and less defined in other places in the image that are have a higher degree of linear polarization. And then the final thing to kind of note there is that even if we could retrieve these neutral points really well and strictly define them, in remote sensing applications, because there's no signal there, the atmospheric polarization signal is going to automatically dwarf it. It's going to be nothing compared, because it starts off as nothing. Any signal from the atmosphere is going to override it. So it would be, I can't envision how those neutral points would be observed from space for comparison. So what can we do? And that's kind of why some of this presentation has been highlighting these Q equals 0 lines and these U equals 0 lines. Of course, where they intersect, we have 0 degrees of linear polarization, but a Q equals 0 line does not have to occur at the degree of linear polarization of 0. In fact, if you look at the top of the image here, it looks like we have about 23% linear polarization, and that's because there's a high contribution in U. And so we still have linearly polarized light. And also that kind of region at the top of the image, that's away from the shadow of the instrument, which I think is going to help. And it's also because the degree of linear polarization is higher in remote sensing applications, the atmosphere is going to affect it less than it would at neutral point. So that's a few reasons why that might be useful. And to kind of dig a little bit deeper into these Q equals 0 and U equals 0 lines, I have this plot here, which is of Q, but I'm showing all 3 cameras so we can kind of see the spectral variations. And then I show the 2 models, the single scattering model, Voss and Fry in the black and Rayleigh scattering in the white. And this kind of works against my point, because in this region here, I was saying that might be a really good place of interest. But if you look at the 2 models, there's not that much difference between the 2s. And also the spectral channels, especially if you look below, they're kind of overlapping each other. Some of that overlap and lack of variation is because we're in the meridian reference frame. But I think still, though, it certainly looks like there's less variation there than, say, this region. But this, again, is the region I'm saying is difficult to measure due to the instrument shadow and just overall low polarization signature. But we see this is where a lot of the differences between the 2 Mueller matrices used show up. And also there's a lot of spectral variation. But that spectral variation could be noise, or it could be something useful to exploit. And so I'm just highlighting those principles there. And that kind of brings us to the end of this talk. I can't believe I'm getting this behind me. But in summary, Pixpol measures the polarized distribution of the downwelling light at the 500 nanometer wavelength. It also measures the upwelling light in 3 spectral channels, the blue, green, and the red. And then given these polarimetric retrievals from Pixpol, we've accounted for how the higher viewing angles might affect things once we account for the distortion of a fisheye lens. Also, we've kind of shown how our measurements in the open ocean compare pretty well with a single scattering model using the Voss and Fry Mueller matrix. But the turbid water location shows a very different signal, and that's probably is going to be easily identifiable. And finally, I think there should be more efforts in looking at the lines of Q equals 0 and U equals 0, because they probably do summarize a lot of the distribution of polarized light, and there's probably more to do with those. Then it's time for just to say my thank yous. Of course, I thank Dr. Voss for all his encouraging support and advice and all the time he's given me. Dr. Gleason for his help with the models and all the programming nuances, which of course show up a lot. And then especially as well, the Moby team, especially the ones out in Hawaii. I got to spend some time out there, and it was a real privilege just to see them work and try to learn as much as I could. They had, I don't know to call them tools or toys, but they have a lot of resources, and it was really nice to learn from that. And thanks to Dr. Twardowski for the participation on this cruise, and Dr. Jeremy Wardell for just leading me to some experiences outside to what my lab provided to see kind of the full scope, or a much fuller scope of the ocean color field. And then finally, my NASA fellowship was supporting me during this work. And just to kind of end on a little bit of a personal slide, this is just my fiance and I out in the Keys. I kept a little 15-foot boat down in Key Largo while I lived here, and it was truly beautiful. I love the ocean, and it's a privilege to be able to study it, but it's also a very nice thing to be able to go out and enjoy. And this day in particular was really beautiful. You can see our boat in kind of the center, the small one. That sailboat's not ours, but it was really, but it was a really beautiful reef, and we really tried to get down there as many times as we could, and each time it was just as spectacular. So thank you, everyone.